Hello, boys and girls. We are on lab 12.8B, or A, I'm sorry, 12.8B, and in your lab books. And on that page, you have a picture of a bunch of stars, and then below a bunch of telescopes next to a definition. And so what we're going to be doing is really matching the definition to the correct stage or part of a star. Now, I couldn't draw the telescopes and the star. The only star capability they have on here is a stamp. So I couldn't really put it in, but here, I'll put some stars next to each of those so you know. These are the ones inside the stars. And then the definitions I have on the right over here, all of these are what you have in the boxes next to the telescopes. So on your page, what the directions say to do is to read the definition and then write the number of the star, or the number from the inside of the star that matches that definition, above the telescope. So right above the picture of the telescope, you're just going to write a number 1 through 14 as we match up the definitions with the part of the star cycle. Okay, so let's go ahead and start on this. So our first definition, and as I read it, just find it because they're kind of scattered all over the page. They're not in an order, so I'll read it a couple times, find the box that we're in, and then we will match the correct number to it. So the first one, which is on the far left top, a small, hot, very dense star. So if we think back to the diagram that we drew for our lab a couple days ago, where it started, you started with your nebula. Okay, it looked something like this. Okay, this chart, if you want to go back to this chart to help you remember. Okay, when we started this, a star begins in the nebulous, and then from there it can either become a medium to large size star, or it becomes a giant or a supergiant star, and they take very different paths from there. And so we're first dealing with a small, very hot, very dense star. So if we look at the definitions that we have over here, the words we have: apparent magnitude, luminosity, nebula, main sequence, white dwarf, neutron star, binary star, pulsar, star cluster, ellipse, giant, supernova, exoplanet, and absolute magnitude. Okay, now a small, that should give us a hint, hot, very dense star would be a white dwarf. So white, when you think of the color white, in a fire, if you see white in a flame, that is the hottest part of the flame. And dwarf obviously means small, smaller than average. And so a small, hot, very dense star is going to be a white dwarf. So above that telescope with the definition, we're going to put a number 5 right above that telescope to match with white dwarf, which is in star number 5 above. All right, the next one, a rapidly spinning neutron star. This is right to the right of the last one we did. A rapidly spinning neutron star. This is going to be a pulsar, so number 8. So you can go ahead and write a number 8 right above that telescope. And remember, a pulsar star, because it's spinning, it looks through a telescope like it's pulsing, like a heartbeat, because of the spinning rotation of it. And so that's why it's called a pulsar, because it looks like it's pulsing. All right, on to the next. A group of stars held together by gravity. A group of stars held together by gravity. This is below the first definition that we did. And this is going to be defined as a star cluster. Okay, so that is number 9. So you can go ahead and write number 9 right above that telescope. A group of stars held together by gravity. So you have stars out in the universe, and these stars in particular are held closely together because of the gravitational pull of each of them. And so just like our planets are held in our solar system by the gravitational pull of the sun, these star clusters are stars that are held together in a grouping because of the gravitational pull between them. Okay, so when we see really bright stars in the sky, that actually could be a star cluster that's millions of light years away. But it's pretty fascinating that what we see and what we perceive is in the sky could be completely different and on a much larger scale than we could ever wrap our minds around. All right, on to the next one, which is right to the right. The explosion of a massive star. The explosion of a massive star. This is a supernova. So this is going to be number 12 star. A supernova. A supernova is an explosion. Remember, when you get from a giant star to a supergiant, it eventually is going to explode. And from that explosion comes three different things. That explosion is called the supernova. And from the supernova, you can have some materials expanding into space and forming nebula. You have some turning into neutral particles, which makes a neutron star. Or you have some where the particles are imploding on themselves, concaving on itself, and you end up with a black hole. Okay, next definition. And this one is to the right, up along the top. An extrasolar planet. Extrasolar planet, this one should be easy because there's only one word that has planet in it, and this is exoplanet. So this is number star 13. An exoplanet is an extrasolar planet. So one that is outside our solar system, but it still stays drawn because of gravitational force. The next one to the right of that, an elongated oval shape. And so remember, when we were talking about theories of our solar system, there was the theory of a geocentric solar system where the Earth was in the middle. There was belief that we moved in complete circular motions around the Earth, or planets did, and then it shifted to being a heliocentric model of the sun being in the center, and this is what we still believe today. And instead of having those round circular orbits around the sun, it was later discovered by Kepler that it's actually an elongated oval of an orbit around the sun every year. And so what is this called? The elongated oval shape that a planet travels around the sun. This is going to be an ellipse. So number 10, star number 10, an ellipse. It moves in an elliptical manner around the sun. So that was number 10. You can write above the telescope next to an elongated oval shape. All right, the next one, which is straight down from it, the rate at which a star radiates energy. So the rate, which can be calculated, the rate at which a star radiates energy. This is the luminosity. So right above that telescope, we're going to give it a number 2 for star number 2, luminosity. Luminosity is the rate at which a star radiates energy. Okay. The next one from that, which is to the left of the box, a large cloud of gas and dust in space. Now, this is back at the beginning of our star life cycle. This is the nebula. This is also a stage that we see pop up a lot during the stages of a star. Nebula, as stars expand and they break off pieces and then form new sections, they kind of reproduce or split apart to create new stars. They're creating new nebula. And from the nebula becomes the gravitational pull between those particles of dust and gas in space, and then new stars are formed. And so nebula is something we see at the beginning, we see it in the middle, We see it at the end when it comes to giant stars after a supernova. So this is something that continues. Without nebula, you don't have new stars. And so in order for the star life cycle to continue, there always has to be new nebula from old stars. The actual, so we are on the next one, which is to the far left, the actual brightness of a celestial object. So yes, we can see it with our eyes, but what is the actual brightness? How do we measure the actual brightness of a celestial object? This is the absolute magnitude. So numbers 14. The absolute magnitude. That means you can use a formula to find factually how much energy is being, or brightness is being radiated from this celestial object, be it a planet, be it the sun, be it a moon. How much is actually being given off by that planet? So absolute magnitude means it's factual. Okay, now to the right of that box, we're going to the next definition. Two stars revolving around each other. So just two stars that are revolving around each other due to the gravitational pull between them. This is called a binary star. So we're going to put a number 7 right above that telescope. Two stars revolving around each other is a binary star. Now, when I think of this word binary, I think of computers. Computers run off something called a binary code, and a binary code is a system of ones and twos, and maybe zeros if I remember correctly, but it's a coding of computers that allow them to work the way they do, and it's all out of a pattern of the number 1 and 2. And so when you think of binary stars, you have two stars that are revolving around each other. Bi means two, like a biannual fair would happen twice a year. And so the prefix bi means two. So binary star would give you the indication that these are two stars that are with each other all the time. Okay. Next to that on the far right, the small, dense core left behind after a supernova. So the small, dense core left behind after a supernova. This is going to be called a neutron star. And remember, the neutron star, it's called neutron because it's neutral. After the explosion, you end up with particles in space that are neutral. They're not positive or negative, they're neutral, and that creates a neutron star. Right below that, in your bottom right-hand corner, the measure of a celestial's body of brightness as observed from the Earth. Now, farther up, we said the actual brightness of a celestial object. So that means we used a formula, we used technology to figure out the specific factual amount of brightness coming from a celestial object. Now we're talking about the measure of a celestial body's brightness as observed from the Earth. So just what we can observe, not using a formula, not using high-powered telescopes, or maybe it does, but it's more of observation rather than factual formula. And so this term is called an apparent magnitude, and that is number 1. So you can put a number 1 right above that telescope next to the definition. The apparent magnitude. So if you say apparently, that would mean this is what I've heard, or this is what I assume based off the information I have, but it's not necessarily fact. And so when it comes to this, what we can view of the star with our eyes here on Earth without having the formulas, without having the high-powered technology, we can assume the luminosity of a star, or the amount of energy or brightness given off by a celestial object, by the apparent magnitude, which still holds a lot of weight in the scientific field and has a purpose. A large bright star with low surface temperature. So a large, that should give you a hint, large bright star with low surface temperature. This is a giant star, and so we're going to write 11 above that telescope. And remember, the larger the star, typically the cooler the star is. You have white dwarfs that are very small, but they radiate a lot more energy and light than the larger stars do. So although it be large, it may not have as much energy as a smaller star. And the last one, where most stars are found in the HR diagram. So if you remember that HR diagram we did a couple days ago, it kind of places on the scale where categorizes different stars. Is it a white dwarf? Is it a main sequence star? Is it a giant, or is it a supergiant? If you remember, our own sun, which is a star, falls in that main sequence of stars. It's a medium to large star, and it falls in that main sequence. And so we're going to look over here on our chart to find our final number, and that is going to be number 4, main sequence. The main sequence is an area of stars that are most common that we have viewed thus far about stars. All right, great job, guys. That is the only page of the review we're going to be doing. You do not need to go on to 12.8b. So as we wrap up this section on stars, next week we're going to be going into the human body. And so as we wrap up stars, take some time to, again, go over the links that I sent your parents for YouTube videos, or go do some exploring with your parents' permission yourself to find some videos about stars, the life cycles of stars. If you want to do some research on black holes, what is a black hole? What is a supernova? What happens after a supernova? These are all things that would be great for you to do some further research on. So I hope you enjoy learning more. Ooh, that's really close now. I hope you enjoy learning more about stars. And as it's getting warmer, if you have a telescope, take it outside and go look at the stars at night. See if you can see any irregularities with the telescope that you can't see with your eyes. And see if you can find some information on what the constellations are, if there's actually planets that you're seeing. So have fun with that, because it's really fascinating, and we have a wealth of knowledge at our fingertips. See you later.